In the density of liquid labs, we're going to calculate the density of water, Coke, and Diet Coke, and we're going to determine and calculate the number of grams of sugar in a can of Coke based on the premise that regular Coke and Diet Coke have the same ingredients minus one has sugar and one doesn't. So under that premise, we're trying to calculate how many grams of sugar, and this will help us with calculations and conversions and significant figures and measurements, and it's the final lab of the first module. So very simply, we're going to get to the data collection, but before we do so, we should have a good look at some previous experiences you probably already have had with Diet and regular Coke in water. If you haven't already done so, get these objectives that are listed here. In this lab, we're going to be looking at density, a physical intensive property that we've used previously to identify different compounds, including the aluminum that the soft drinks in front of us is being contained in. And what we're going to do is we're going to compare the soft drink's density with water, with the liquid behind it. And this is something you may have noticed at a party or in a cooler of soft drinks where you have the diet and their regular forms, that their densities are different. Okay, so let's put in the Coke, the regular soda here that has normal amounts of sugar, and what I'm trying to do here is get the bubbles that could collect under the can away, and we should see that our can sinks to the bottom, which is telling us it's a bit more dense than water, which makes a lot of sense. It's got a lot of sugar in it. And then we have our Diet Coke, or soft drink here, that does not have the sugar. So again, make sure that we get all the water that doesn't collect on the bottom of the can out, and we should try to see if we can make it sink. And we can see that it's pretty darn buoyant. No matter what we do here, that can floats to the surface. So if you ever, again, we're at a party and you open up the cooler and you see the Diet and the regular sodas, the Diet will float to the top because it's less dense. And you can see there's 0 calories listed here. And one of the reasons why it's 0 calories is because they use a sweetener instead of the sugar, the carbohydrate, and that sweetener does not have any nutritional value. So in this lab, we're going to use the premise, because the point of the lab, yes, is to calculate the density of both the Coke, the Diet Coke, and the water. And from our observations here, or past observations, we should know that the Coke should be heavier, okay, at least a higher density than the water, and the Diet Coke at some point seems to be less dense than water, and that's also very troubling to some students. Do not forget that there are CO2 gas, okay, trapped inside here that's messing with this density as well. So don't forget about the carbonation. So that's an important observation. But the premise behind this lab is that the difference between these densities, okay, we're going to test this premise, is that this has sugar and this doesn't. So we're going to say that the Diet Coke has the same ingredients as the regular Coke minus the sugar. Now, we know that's limited in the sense that there is sweetener here, and we're not investigating the mass of that sweetener, but clearly there is a difference, and we're going to come up with that premise, and we're going to basically test that premise and see how well it works, because we're going to calculate through the density how many grams of sugar this has. Again, assuming that these have the same what? Same ingredients, just one has sugar and one doesn't. So we can read the nutritional facts on the Coca-Cola can, and we can see toward the bottom here total carbohydrates is 39 grams, and that's sugars, 39 grams of sugars, and that's going to be our accepted value that we're going to use in our percent error there. In the Diet Coke can, we can see the nutritional facts clearly state that there are 0 carbohydrates. Okay, so the major premise of this lab that we're going to test by trying to calculate how many grams of sugar are in regular Coke is we're assuming that this can of Coke, Diet Coke, has no grams of sugar, and that Diet Coke has, and that's the only difference between them. So before we can determine the density, we're going to have to measure mass and volume, obviously. So let's begin by getting some regular Coke and Diet Coke in here. And the one thing I want you to realize, we have a problem initially in this lab, is that we're going to have that carbonation. We're going to have gas that's in the liquid or dissolved in the liquid, and that could cause some problems for us. So what's really helpful in this lab is to let the Coke and Diet Coke go flat. Now that may change our observations a little bit from what we expect based on water, but it won't change the fact of how Diet Coke and regular Coke may differ. Or does it? Again, we're assuming that they're the same ingredients. So what we're going to do here, alright, is let it go flat for a couple of days so that we're able to better use and measure without the problems. Because in this lab, unlike our first density lab, we're dealing with measuring volume, with a liquid. With a solid, we measured the dimensions with a ruler. Here we're going to need a graduated cylinder, and we're going to have some issues with the space being taken up by the gas. So we're going to let this go flat for a day or so and pick this up, the next day. So we're going to start with water. It's our first data table, and we're going to use a graduated cylinder this time to measure the volume. We can't measure the dimensions of a liquid because a liquid doesn't have a regular geometric pattern. It takes the shape of its container, something very important for the Regents chemistry curriculum. So all I'm going to do is take some spring water, and I'm going to pour it, and I'm going to fill it to the 100 milliliters mark. Now you notice the graduated cylinder has markings on it, calibrations, and those calibrations are something that I'm going to read and make sure we understand how much. Now we're going to have to get up close and personal here to see exactly what my value is. I'm trying to get 100 right on the 100 mark, but we need to understand what that value will be. So I clearly went over the 100 mark right here. So I'm going to take a pipette. I'm just going to pipette out the excess so that I can get to that value. Alright, a little more. Way past it, looks like. And what we're looking to read is the bottom of the meniscus. There's a meniscus when we read a graduated cylinder, and it's a little line that bends because of cohesive and adhesive forces. Cohesive in that the water holds onto itself by H bonds, and the adhesive is that the water actually is attracted to the silicon dioxide in the glass, so it's kind of holding on the sides. It's very subtle, but there's a curve here, and we're going to read the bottom of the meniscus, and we're trying to get that bottom just a touch to 0. So I'm going to grab just a little bit more and see if that makes any difference. Again, it is a big difference in lab, but trying to get, I think right there does it. So we're on the bottom of that meniscus, and now we have 100 milliliters. And if you write 100 milliliters, I'm going to have to take points off in your lab because, wait a minute, if it's 100, then where's my guess? Is my guess in between the 90s? Well, I've got calibrations here, don't I, in between? If it's calibrated to the individual numbers, then let's pretend it was on a 99 in between 99. Then we would go 99 point something, right? So if it's calibrated into the individual milliliters, as I see here, this is 90, 91, 92, 93, 4, 5, then my guess has to be what? In between the individual integers, so now my guess is in the tens place, right? So we're going to guess that this line is right on the 0 line. So we would say 100.0. If you said 100 point, your guess would be in the individual integers, but because of the calibration, our guess is in between the individual single digits. So we have to be out to the tens place. So we record this to be 100.0. In the lab you see it's written there, but that's an important as I'm going to have you measure for me on a test. So now we're going to measure the water, And we're going to measure the mass of the water. We have the known exact volume. We have our 100 milliliters, 100.0 milliliters, meaning the 100.0 is telling me that I have a measurement device that was calibrated to the single individual integers. Remember, that significant figure is so important as we go through the entire course and into AP. Now, how do I measure the mass? Well, you think, well, believe it or not, I've had students do this. They would actually zero out our balance like it is right now, all the riders to the left, and they begin to pour the liquid and then try to find the mass as they poured, and that's of course not what we do here. So you could try to put this on here, but because it's leaning and some of the mass is being used to lean up against this, that would not be a very accurate way to do this. So what we do and employ in physical chemistry labs, we have containers. So what I'm going to do is mass out the container, okay, and knowing its mass, and on your first column or the first line in your data table you have mass container. So we're going to use a 250 milliliter beaker, and something to notice about the beakers, they have little lines in them. These little lines are just for filling purposes. They're estimates. We never measure volume with a beaker. A beaker is a container, so these are not very precise markings. Any case, so I'm going to measure out the container, and we can use that container for the rest of the lab, assuming it's dry and it's clean every time. Okay, so now that I got the beaker all massed out, okay, all zeroed out, let's go take a closer look at what it looks like in terms of the riders on the device. So this is what the riders on the triple beam balance look like when I massed out the container. So make that measurement, make sure you have a unit with every measurement that's appropriate with the triple beam balance and the correct level of precision. Don't forget your guess. Okay, and let's now pour in the water, and of course let's see how heavier it gets. Think about some forms of error that could occur in this lab. Okay, obviously you can see the riders are now unbalanced. Now I have to move the riders from the position I have, and from that position we can figure out the mass of the water. So we have the mass of the container, and now we're going to have the mass of the container plus water. You probably can figure out how easy it is to get the mass of now the liquid. Alright, so I've now rebalanced the scale with the extra mass, and now we're going to get up close and personal again and read the riders. This again is the container, which is the 250 milliliter beaker plus the water. Now we're up close and personal with the riders on the triple beam balance, with the water and the container. Notice for those that's saying, wow, water should have a density of 1, this seems to be a lot less. Remember, density of water is 1 actually at a certain temperature, 4 degrees. So this is a lot warmer than that. It's about 22 degrees in here. So we can expect our density to be a little less than 1. Let's begin with our second liquid, regular Coke. And let's try to get to the 100.0 milliliter mark. And I will pipette out any excess. I'm getting my eyes on pretty eye level and taking out the excess. And now we're going to take our beaker that has been dried out, so there's no liquid to minimize error, and we take our previously clean graduated cylinder that now has a regular Coke in it, and we're going to use the mass of the container that we used for the first one. We cleaned it out, so we can go that route. You may find that to have some error in it as well. So we'll think about that. There's always limitations to measurement and experiments. So now let's pour this liquid in. You already know this mass from a previous massing out. And I'm going to pour 100.0 milliliters of regular Coke. And we're going to go find that mass. Okay, so I have balanced my scale, my triple beam balance, with the container plus the Diet Coke, and now we're going to get up close and personal to read the value. So please make a reading for that value there. That, of course, is the regular Coke and its container. To get the Coke, you can probably guess how to do that. And let's do the Diet Coke, our last liquid. Again, going to the 100.0 mark and then taking away. Notice there is still some fizz, some CO2 into the liquids, and you can again see how that may contribute to the error. Okay, so now I have taken my pipette and made sure that I'm at the 100.0 mark, and now I'm going to fill my container. I'm going to use the same mass in my container. If you think that's an experimental flaw, you should think about that for your errors in your lab write-up. So I'm going to pour the liquid in, same container, we know its mass. And let's go re-zero it out. Now my Diet Coke, last liquid, I've moved my riders and I have balanced it off, and let's get up close and personal and read that value. And there is our value for our Diet Coke. Get that down, write that down, make sure you have the right level of precision for this device. I've been using it the entire day, or at least lab, so it should be this similar in its precision, and make sure there's a unit associated correctly with this device. And now we have all the data we need to calculate the densities and get to and calculate and determine the mass of the Diet Coke in terms of its sugar. So I want to walk you through the calculations in this lab, at least for one liquid, and let's get started. We have the mass of the container, okay, and that's 110.840 that I got from the video, and I got 209.720. That's the container and the water, the liquid. Okay, so to get just the liquid, I've got to subtract out the container. So I'm just going to rewrite this, and it's always a good thing to put all your work in your lab, okay, so you can see all your calculations. In more formal labs, we'll have a calculations page. So I'm going to subtract my 209.720. I'm going to subtract, I guess, 110.840 from that. Okay, now of course you could have put that into your calculator, and what you would get is 98.880. All right, and if you were to put it in your calculator, you actually would get 98.88. The calculator wouldn't put a 0 in there, would not put a 0 right there. Okay, and you might be tempted just to write what the calculator says. The calculator is not going to pay attention to the measurement devices that were used to get these numbers. Okay, and we know that when we subtract numbers, we're following what we call the precision rule. And the precision rule is that we're going to round off to the least number of decimal places. So since there was 3 decimal places in this number and 3 in the second, we need to round off to 3 decimal places. So our value is going to be 98.880, and make sure I have a unit. Okay, there. Have a unit that tells me something about the type of substance or matter that I just measured. So 98.880. Okay. Now to find my density, all I'm going to do here is I'm going to take my density formula, and notice it says show all work grams per milliliter, so density is equal to mass over volume. And then so the mass that I have after subtracting the container to get the fluid is I got 98.880 grams over the milliliters. Now notice in this lab we're using milliliters, but you should also know that a cubic centimeter is the same volume relative. It's the same amount of fluid that takes up that space. So 998.880 divided by, guess what, the volume, which is 100.0 milliliters. Okay, you notice we're going to get grams divided by milliliters here. Okay, and so you're going to put that into your calculator. All right, and when you divide by 100, okay, you're going to move your decimal place over a couple of places. And what we get here is 0.98880. Now your calculator might have stopped at the last 8 and didn't put the 0 in, but now what's our rule when we divide or multiply? Well, there's 1, 2, 3, 4, 5 significant figures, and here there's 4. The rule with division is the accuracy rule, and we have to make sure that we're following that rounding wise. So we're going to minimize, or we can't overestimate our value based on the weakest link. So this has 4 significant figures. Why? Well, because ending zeros count if a decimal point is present. And this one is 1, 2, 3, 4, 5 significant figures. Why? Ending 0 is here and there's decimal point. So 5 sig figs here, 4. Answer has to have 4. Look at my 0, it's less than 5. So my value here is 0.9888. And that's the density of my water. Okay? And that's the density in grams per milliliters. Now, an interesting conversion here for number 6 that always gets people down and out is they look at the grams per liter. They say, oh, well, a liter, okay, is 1,000 times, okay, different than a milliliter, right? A liter is that suffix, and the prefix is the miller, okay, so it's right in there, that liter. So we have a milliliter, so you think, wow, this is going to get smaller by a lot. So some people would put 0.000988 and that'd be wrong. The way to do this is to use your units. Watch what I'm talking about. Take your point. All right, I'll try to do this like this. 0.9888, and that's, what's the unit? Grams over milliliter. And then we're going to times it. This is a conversion. I want to get rid of milliliters. So like we did before, we're going to cancel out, except now, because the milliliter is starting on the bottom for this density unit, I have to write it where? On the top. Okay, and then I want liters, right? Because I want grams per liter, so the liter goes on the bottom. A little bit different than we've seen it before, but if you're just using your units and the idea of canceling out the units, it should work. So we need some numbers here. Well, we know that a liter is a bigger unit than a milliliter. So it's going to take, with a bigger unit, or I should say a smaller unit, it's going to take a lot more. So between a milli, which is 1,000th, and a liter, there should be 1,000 of these, okay, per one of these. And you can see the milliliters cancel. And I get a unit that's grams, because grams are left, over liter. Okay, so we're going to times it by 1,000, not divide by 1,000. It's not going to become 0.00. Okay, so we're finding the grams per liter. So we times it by 1,000, and what you get is 988.8 grams per liter. Okay, and you say, well, how do you know how many sig figs? Well, remember, in a conversion, if you start with 4, you should end with 4, because these are not measured values. Everything's coming back together with this nice lab. These labs take into account everything you've learned here. So we want to put our value in is 988.8 grams per liter. Okay, and now you understand, and it's pretty intuitive, I think, grams per milliliter. Well, milliliter is tiny, so it's not going to be many grams per milliliter. So if you're going to make your volume 1,000 times bigger, the mass is going to be 1,000 times bigger. Okay, and you're going to do this for the rest of the 3. And again, you may say, Mr. Grodsky, wow, the density of water isn't 1. or 1,000 grams per liter for water. And the reason is water has a density of 1 at 4 degrees Celsius. Okay, so this is a lot warmer at room temperature here. It's probably like 22 degrees Celsius in the lab today. Okay, so you're going to do this for the next three liquids. So I just want to go over quickly the conclusion calculations, because we want to calculate, remember, the number of grams of sugar that are found in a 355 milliliter can of Coke. So I'm going to quickly go over how to do that. Now, how do I find a mass of a 2-liter bottle of Coke? Because we didn't have a 2-liter bottle of Coke. What do I have? Well, from your calculations, you should have grams per what? Milliliter, or grams per liter values. Well, if you already have the density in grams per liter, and I want the mass of a 2-liter bottle, can you guess what you're going to do with that? Yeah, you could times it by 2. And that would be the grams or the mass of a 2-liter bottle of Coke. Now, if you wanted to use the grams per milliliter, in a 2-liter bottle, you should know in 2 liters there's how many milliliters? And you would times that by a number. Okay, so that's pretty straightforward. And number 3, they want the number of grams of sugar that are contained in a 2-liter Coke bottle. Well, remember our premise. The premise is that a Coke and Diet Coke have exactly the same what? Ingredients except the sugar. So I would take the 2-liter bottle of Coke mass that you have, right? This is the Coke. It's 2 liters. I would do the same thing for Diet, right? I would do the same thing. I would take my grams per milliliter of the density of Diet Coke that I calculated, and I would do the same thing. And then what do I do with these 2-liter masses? Right? One has sugar, one doesn't. How are we going to find the difference? Oops. Okay. And now you have the grams of sugar in a 2-liter Coke bottle. Again, with the assumption that the ingredients are the same. Now, this is going to give you grams of sugar. Now, number 3, how many grams of sugar are found in a 355 milliliter can of Coke? That's the can of Coke that we used in this lab. Well, a proportion. If you know the grams of sugar per what? 2 liters. What's the gram proportion? What is going to be for 355? So, right, if you have whatever value here, grams for 2 liters, and if you've got to keep in the same unit, so 2,000 milliliters, how much would it be for 355 milliliters? Okay, and there's your answer. Percent error, well, you know what formula to use. We've used this before, and we used the can of Coke in the video. Go back to see what value it was and see what you get here. And then for number 5, based upon the descending order of the densities, so give the densities of the 3 liquids and list them in order of descending order, best to worst or highest to lowest, and give the reason. You can think about that demonstration in the water. And that's the lab. Now, what you're going to find that probably this number will not be very close to the can. It doesn't make it a bad lab. It just means that the premise that we're really testing doesn't work out very well. There probably is some differences between the ingredients. Who knows? So the next part of this would just be a conclusion. In the conclusion, all you're going to do is tell me what you found for the 3 liquids, their densities, the grams of sugar you found, and then the percent error. And then in the second part of the conclusion, very simply, just list the errors, and there's a bunch of them along the way, along with what's wrong with the major premise, and you're done with the lab.